Now we will talk about the globe lemma. Before we learned about regularity lemma. And we use it to solve some problems in extremal number. Basically, we learned about the embedding lemma. That and use the regular lemma, and then if you have some regular partition, say 3 of them, then we can find some small h whose chromatic number is 3, which is 3-part type, and you can find this copy of h in G. Or rather say that you can embed this into G. So you map the vertices in an injective way so that the H is mapped to H. So towards your embedding. So now we are considering Dirac type action. About finding panning subgraph. One natural question is, can we use the epsilon regularity to find the spanning subgraph? So what's the easiest case? When you have say, what's the simplest spanning subgraph, which are perfect matching. Let's say you have a epsilon regular pair, say epsilon D regular. So bipartite graph on between A and B. With both have the same type n. And natural question is, does it contain a perfect match? But we know that it may not contain perfect match. Again, these epsilon D regular conditions are global conditions. So that there could be some isolated vertex here. It could be still epsilon D regular with the isolated vertex. So there could be some isolated vertex, so it may not be. But so in order to obtain perfect matching, we need some local condition. So as we saw before, we know that if minimum degree is large, say certain number, like epsilon n, then let's be safe to make it a bit bigger, to epsilon n, then it contains a perfect match. So we want to discuss some stronger notion stronger than epsilon regular, which also ensures minimum degree. So let's see a graph and disjoint pair of A and B offsets of vertices is, we call that this is epsilon D superregular. If it is epsilon okay, let's write it this way. Epsilon D regular. And say that the neighbors, each vertex has enough neighbors on the other part. So for A, vertex A in A and P in B, this vertex A has minimum, degree at least T minus epsilon times B, side of B, and B had a number of neighbors is T minus epsilon times size of A. So oftentimes, they also put there are different definitions. The oftentimes what they define is that it's bounded from below and bounded from above at the same time. So if I write A equal B plus minus C, that means A is M most B plus C and L is B minus C. So instead of writing these two inequality, I will just write here. So this means that not only you have a lower bound, but also have upper bound. But these two definitions are roughly same. Meaning is that if we only have, this is stronger than that. So this implies the above one. And when we have above one, and if you know that this is epsilon d superregular, then you can show that most of the vertices have the upper bound as well. And only the small number of vertices might have a larger degree. In that case, for each vertex, it stands dot edges. And then out of this edge, you uniformly random choosing a set of the D, A, D, right number of vertices. So you randomly choose you randomly delete some edges so that give me a moment. Yeah. So you randomly delete the edges so that this has the correct degree. They will lower some degrees on other vertices as well, but you can show that with high probability, it doesn't lower much. So that if this holds, if this holds, then you can show that this holds with a slightly bigger epsilon. Say 10 epsilon, epsilon becomes 10 epsilon, then this is still true. So you can use either definition. So it's essentially equivalent. And in most of our application, we just, make sure that epsilon is sufficiently smaller than D. For epsilon or 10 epsilon will not matter too much. Okay. So now natural question is that just like we used this embedding lemma before, and we combine it with the regularity lemma to find the, small subgraph in G so that we can deal with the extremal number problem. Can we prove something that can be combined with the regularity lemma so that it helps us to find the penny subgraph? Indeed, there is this lemma, which is called the blow-up lemma. So what is it? So suppose that, of course, n is sufficiently large and epsilon is sufficiently small compared to d and delta, 1 over delta. And you have several cases, so several objects to consider. So let's say R is a reduced graph. So this is a graph on the vertex set, bracket R. It's that it has a bounded maximum degree. So its maximum degree is bounded. So this will be our reduced graph. And okay, we will write G and the H. So H is the graph that we want to find inside of G. So this is like host graph and this is like guest graph. And then you want to embed it H into G. And let H be an n vertex graph. with it has vertex partition x1 to xr. And this X respects the structure of R, meaning that if R is like, say, this, let's say this is R, and this is 1, 2, 3, 4, 5, then what X does is that you have X1, X2, X3, X4, X5, then there are only edges between these, which correspond to the edges of R. So, meaning that okay, with this also have a maximum degree most delta, and the number of edges. So there are edges between xi and xj only if ij is in R. So that means if this holds, then if there is an edge, then ij is in here. Maybe let me write with the if such that it implies. So that's H. And then G is the host graph. This is again n vertex graph. Yeah, I mean let's not use this as n vertex graph. So let's denote x as the size of, I mean n as the size of each xi and pi. So this is the graph with partition, the vertex partition. P1 to PR such that each pi has same size as xi, then this is exactly n, and each pi bj is epsilon t plus superregular. So, and epsilon say t prime plus, we say that this is superregular, means that the epsilon t superregular or some t bigger than or equal to t prime. Let's write it this way. So this is superregular with a density bigger than d for all ij in this R. So what do we know? So let's say again R is 1, 2, 3, 4, 5, then H is what? H looks this way with x1, x2, x3, x4, x5. Then G is like this is epsilon regular, epsilon regular, epsilon regular, epsilon regular, epsilon regular. P1, P2, P3, P4, P5. In this setup, what's the conclusion? Then there exists an embedding pi of H into G such that each xi maps to pi. So you can find the copy of this inside of G so that these vertices correspond to this vertex. These vertices correspond to this vertex. This corresponds to this. And this corresponds to this. So this is the flow lemma. Maybe you might want to read it again to understand the statement and get more familiar with it. So there are some remarks. So it can be strengthened. One is that this partition, I mean, x1 and xr and b1, br, we assume that they are equipartition, but it does not have to be. So as long as each they set has sides between alpha and the n over alpha inverse, I mean n over alpha, or alpha not too smaller than, I mean, as long as epsilon is sufficiently smaller than alpha, it is okay. In fact, I mean, this does not have to be equality. So inequality is fine. But this case implies that by adding some isolated vertices in H, so we can just write it this way. So here we assume, for our convenience, we assume everything has same side, but it doesn't have to be, as long as their side is not too asymmetric. And also, it can be strengthened. So for each I and the vertex x prime I, which is subset of xi, of size say n most epsilon n. So let's say you have a small subset. What we can do is we can roughly specify where x in those sets should be embedded. Meaning that more specifically, for all x in xi prime, we can even specify that say v prime x in the pi, which is not too small. Say t prime or pi, or some, again, t prime, where the epsilon is much smaller than t prime. Then we can find an embedding pi of h such that the image of this x is indeed in t prime x, or all x in this x prime I. So what it says is that for some small number of vertices, you can even specify where it should go. So, and this statement is actually stronger than you think. I mean, here, for each vertex, you roughly specify where it should go, right? But actually, you can exactly specify them as well if we know this above one. How? Let's say you have H. You have this. Then you have G. What you can do is, if you have this vertex, say Y, and this vertex X, and G, you can decide, let's say this vertex has to be mapped to here. Okay? So you specify that this vertex has to be mapped to this specific vertex. In that case, what can you further to do is you take a neighborhood of this and neighborhood of this. Because of superregularity, these are not so small. What you say is that, okay, this x has to be mapped to this. So let's say this that is b prime x, and then this that is b prime g. So these are already embedded. So what you do is you forget this. So you delete this. So you don't have to embed it anymore. So for each neighborhood of this, you take it that this vertex have to be mapped to the neighborhood of this vertex in here. So this is deleted, but we still know what set this is. The neighborhood of this in this V2 and V3 state. And you specify that this has to be mapped here, this has to be mapped to here. And as this, the side was most epsilon n, you take a neighborhood. So there are more than one vertex that you do that. And the neighborhood, how many of them? M of delta times epsilon n, which is still small. Delta is, just a number. Epsilon is much smaller. So this is very small number times n. So if we know the above statement with this epsilon, instead of epsilon, say you use the delta epsilon as the epsilon here. So here, this epsilon is delta epsilon here. Then still it's a small number. So this statement holds. So as long as, okay, here what I didn't say is that if you want to say this u prime has to be also mapped to be u, and this has to be mapped to u, and then this has a common neighbor. And then it could hold that these two specific vertex might not have a large common neighborhood. Then, specifically, we cannot specify them to be embedded to here and here. That's not possible. So as long as, the vertices that you want to specify are distance LX3 away, then it's fine. Anyway, so this is the additional feature that we can have. But yeah, we will not talk about, not including the statement here, but that's something that we can do. And one thing to notice here is that this R has to be the graph with the bounded maximum degree. And later we want to combine this with the regularity lemma, right? But once you apply the regularity lemma, then what will happen is that you get the epsilon regular partition, but the number of parts are large. R is very large. That's the regularity constant. We learned about that this is power type. Epsilon here. So in this regularity partition, you cannot apply the blow lemma. So there are actually two reasons why it cannot apply. One is that its maximum degree of R is usually, if you graph it, then that's some constant time R, which is too large. That's much larger than 1 over epsilon. And second is that these are not super regular. The pairs are only epsilon regular, but not super regular. So later, usually what you do is that you consider the regular reduced graph, and then you find the subgraph R prime over R with a bounded degree. So instead of taking all epsilon regular pair, you only take, say, when you take your R prime as Hamilton cycle, then you only consider about these epsilon regular pair, and then forget the other part. Then this satisfies. And then you move around the vertices to make sure that these are super regular. You cannot make too many pairs super regular, but the small number of pairs super regular is possible. So for example, this vertex, and then if you consider all epsilon regular pair from here to here, then you cannot make them all super regular, but only two of them, it's possible. How? you take this and then, okay, there are some vertices with 2 row degree, and then you delete. You take this, if there are vertices with 2 row degree, you delete. And most of the vertices are still remain there, then you have a minimum degree condition. That's possible. But if you want to do it, say, r times, and every time you delete like epsilon fraction, and then you make everything super regular, then you have to take the r times epsilon fraction, but r is much bigger. So this is bigger than 1. So you might have to delete everything, which is not good. Okay, so that's the rough remarks and what we will do later. Right. And maybe we briefly discuss about how you can prove this problem. So there are, two proofs. One is by Komrosh, Darkod, and Temerity, who originally proved this problem. In 1997. And then there is another proof by Roden and Luchinsky in 99. So we will discuss about this proof. So basically, the Komrosh Darkod proof is that when you have a superregular pair, you choose one vertex by one vertex. You greedily take one vertex here and decide where to go. Take it one here and decide where to go. And when small fraction of vertices are left, and small fraction of vertices are left, and you have to decide how to map it. You use some sort of Hall theorem to find the perfect matching that maps everything to here. And you repeat for, each step. And that's how roughly this goes. In Roden and Luchinsky, they decide in one go how to map this to here, this x1 to b1, and then you decide how to map x2 to b2, all one together. So we will briefly discuss about this Roden and Luchinsky proof. So let's consider partial embedding. I of h into g. And what you do is h, you have x1, x2, x3, and then b1, b2, b3, g. So how do you do it? What do you do is you consider a candidate sequence. Say A. What does it mean? Meaning that the A and B are in edges of A if embedding X into B is okay. Like extends the partial embedding high into another partial embedding. So what? Initially, when pi is empty embedding, then what? How does A look like? So these are complete bipartite. Anything here can be embedded to here. This cannot be embedded to here. That's not what we want. So any vertex here, you have an edge. So this is initially discharge union or complete bipartite. And what you do is first you want to find the perfect matching here. So that's like how you will map And then you will update it. How? So now this vertex has a neighbor here, and this vertex has another neighbor here, and this is mapped to here, B, X. Then you consider its neighborhood and then its neighborhood. And now this vertex has to be mapped into a neighbor of this because this is already embedded. And in order for this edge to be embedded here, this has to go to a neighborhood. So you delete every edge from here to here. You only keep the edges from here to here. And then same way, this now have edges to only here and here. And let's say there is an edge between this as well. And next time you find again perfect matching in this candidate graph. And then let's say this vertex is embedded to here. Now what? You consider this vertex and then see what's its neighborhood inside of this red one. And then now this candidate graph, again you delete all the edges from this and this part, and you only keep the edges between this to this purple part. And so on. And you take next matching. So that's roughly what you want to do. So in other words, if a vertex X has already embedded neighbors x1 to say xi, then the neighborhood of x in A is same as the intersection of all the neighborhoods of this. So, and each time what? You have a graph A, in each component of A, you take a perfect matching. And you take the perfect matching so that this updated A is still good. And in order to ensure that this can be you can keep doing this, you make sure that you choose this perfect matching so that the next, after updating with respect according to this perfect matching, everything else here has the perfect matching. Then you want to keep go. And in order for that, how do you choose this perfect matching? Is that you want to choose it random way. You want to use perfect matching random. For that, this lemma is useful. So suppose that n is definitely large. C is some small number much smaller than epsilon. And let's say you have a other number as well, epsilon prime, and say d1, d2. Okay, you can take epsilon prime being much smaller than the other two, but okay, so that doesn't have to be. That's usually in the application that we assume that that's additional condition that we don't have to assume to prove this lemma. But anyway, so this is what you know. Then let's say let P be a epsilon deregular graph. With I partition a V1 and V2, and both of them have the same size n. And it is a superregular in a stronger sense, meaning that the degree of each V is V plus minus epsilon n for all V. So we also assume the upper bound. Then what happens is that if F is a subset of V1 and T is subset of V2 with the size exactly D1M and D2N. So meaning that these are not too small. This D1 and D2 are not too small, and I mean epsilon is much smaller. So these are specifically much bigger than that epsilon. Then what happened is that if you say that we choose a perfect matching, sigma of G is chosen uniformly at random. Meaning that you find all perfect matching, 1, 2, 3, 4, you count it. Let's say there are 1 million of them, and you choose one uniformly at random among these 1 million. Each perfect matching is chosen with probability 1/1 million. Then what happened is that you count the number of edges of this matching between S and T. Let's say you have V1 and then V2, and you match U with the sigma U and B with the sigma B, and so on. And if you have F and T, and some could be mapped between and some could be mapped outside, you only count the number of edges between S and T, then it's like almost as expected, almost as the expectation, and probability is at least 1 minus C to the n. So here again, we didn't put any restriction between constants. I mean, which one is bigger or which one is smaller. But in the application, we will consider this case. We make the n much bigger. In such a case, this is the exponentially small number. And okay, so what I just said is irrelevant. I mean, even if C is small, this is still small. Anyway, extremely, I mean, almost, I mean, the probability that this does not happen is exponentially small. Note that if its G is complete bipartite graph, then what? Then and this random variable actually follows the hyper geometric distribution with the expectation D1, D2n. And what's the hypergeometric distribution? It's like you have numbers from 1 to the capital N, and choose a subset of size exactly n. Uniformly at random. So there are n choose n such set. Out of such sets, you choose one of them with the probability 1 over capital N choose small n. Then you let the f subset is f, and then you let the x be the random variable which intersects with the specific set of size m. Then the distribution of, of such x is called the hypergeometric distribution. And we know that the Cherenkov bound also applied for the hypergeometric distribution that suppose X has a hypergeometric distribution with say parameter n, m, and the probability that this X deviates from the expectation by t is almost 2 times e to the negative t squared over 2n. So this is what we know. And this is, if G is complete bipartite graph, then this is exactly same as this hypergeometric distribution. So this channel of bound implies this, because this is the expectation, this is the deviation, epsilon prime over n. And if you plug epsilon prime over n squared here, then what? That's the exponential of negative epsilon prime square over 2 times n. So this becomes your C. Okay. Okay, it seems that I have put the wrong, I expressed it wrong. So this has to be 1 minus C to the n. Sorry. Right. Yeah, so this has to be the number that's getting close to n. So, yeah. So this is correct. So what I was gonna tell before is that in here, when n is much bigger, and C, so if this one is much smaller than this, then this time it is exponentially small. So we are happy. But if both of them are very small, then this might not be so small number. But this lemma works for any number satisfying this. So in the application, we actually choose n to be much larger so that this inequality holds. Then this guarantees you that this is very close to 1. Okay, and also this lemma, what this lemma said is that for complete bipartite graph case, this is true due to this chain of bound. But even if this is not complete bipartite graph, as long as this is epsilon d super regular with the lower bound and upper bound on the degrees as well, then this holds. And so we need this lemma to prove the blow-up lemma. And then luckily, how you can prove this lemma is that you count the matching. How do you do? It is that you have S and then you have T, and then assume that there are, say, X many, so lowercase X many edges. And then you count the number of edge matchings here, here, and here. So you want to count the number of matchings which has a UX x-axis here. For that, you first show that you first count the number of entire matching in its superregular pair with the maximum degree, almost regular. Its degree are almost regular, meaning that all the vertices have degree between d minus epsilon and d plus epsilon, and it is superregular. And then you can count this. And how do you count this? You know that the number of matchings in bipartite graph is related to a permanent of a matrix. So this is related to permanent of the matrix. So bipartite adjacency matrix. And there are certain theorems for permanent. So there are the ones called Link's conjecture, which is proved by Bregman, and van der Waals conjecture, proved by Seligman and Egorchev. And both of them, I mean, kind of give you a lower bound and upper bound on the number of matching here. And one of them is applied to doubly stochastic matrix, which corresponds to the exactly regular subgraph. But you can actually prove that such a superregular pair contains a subgraph with exactly every vertex have a equal degree. There you apply this to get a lower bound, and then yeah, by doing that you can actually count it. Then for specified edges, now from here to here and here to here, these are like epsilon regular, and these are also epsilon regular. So in here you count the matching, you count the matching, you count the matching, and so on. And you can show that the probability that the each chord is like at most like this. That's what you can show. The rope deck, but that's exactly, I mean, what's happening in complete bipartite graph. In T, you choose just X vertices. In S, you choose S vertices, X vertices, and you match them. And so this is X. And in the remaining one, what you choose the vertices which will be matched to here. And here you arbitrarily match and then try to compute the probability. Then you get this. So this showed that this is almost like the hypergeometric distribution up to certain multiplication. And then you compute what's happening for the hypergeometric distribution, and then you multiply those, I mean, vector, the upper bound on those vector to each bad event, then you can get this lemma. Anyway, so this is some lemma that we want to assume. And there is another useful lemma. So, what is this lemma about? So let's say you want to check whether this bipartite graph is epsilon regular or not. Then how do you check? If you use the definition, then for all subset A prime and B prime, the density between A prime and B prime had to be correct, E plus minus epsilon. The number of edges is like this. But how many choices for this? So they have size at least epsilon n. So there are like 2 to the n choices and 2 to the n choices when A and B have the size n. So there are exponentially many choices, and for each choice you have to count the number of edges, which is quite inefficient. On the other hand, there is this theorem which provides a much more efficient way for doing this. Let's say you have a bipartite graph with vertex partition A and B with that both of them have the same size. Okay, and if technically, okay, this does not have to be exactly equal, but anyway, so if they at least 1 minus 5 epsilon times n to 2 pairs of vertices u, v in A, satisfy the following, then G is like 16 epsilon to the 1 over 5 regular. So what's this two condition? That the degrees are large and their common neighborhood size is not large. So for most of the pair, if these two conditions satisfied, I mean, the first condition only said that most of the vertices have the correct degree. And second condition said that for out of n choose two choices of pairs, most of them have the not too large codegree. The expected codegree, if everything has every vertex has degree Dn, and their neighborhood are like random, then expected size of a common neighborhood size is d square n. And it shows that it's not too larger than that. Then this is epsilon regular with a slightly bigger epsilon. So again, this provides a much more efficient way for checking this epsilon regular. You just have to choose and choose two pairs, and then check how many of them satisfy this. Of course, I mean, this is not exactly equivalent. I mean, you check, this is a sufficient condition. So it's a bit different from checking. So if this satisfies, then this regular. But even if it doesn't satisfy this, it could be still, no, that's a bit different. Okay, let me repeat. So what we know is that if you have a epsilon regular partition, then you can check that at least this many pairs satisfy these two conditions. On the other hand, if this satisfies for this many pairs of vertices, then you can check that your bipartite graph is 16 times epsilon to the 1 over 5 regular. Again, this is loosely equivalent, these two concepts of if this condition satisfying for most of them and the epsilon regularity are loosely equivalent, meaning that it's not equivalent. One does not imply, I mean, it's not like both implies this. So this implies this, but this implies the essentially same thing with the worst parameter. But for most of the problems, I mean, increasing epsilon a bit is no problem for us. As long as we take it sufficiently small, then it gets ruined a bit. It is still sufficiently small. So this can be thought as I mean, like essentially equivalent. Okay, so now we are equipped with this two lemma, which is the important ingredient for proving the blob lemma. And yeah, we will talk about the proof of blob lemma in the next video.